let us start the session. So this topic, if not properly understood, it will be little confusing. So you have to focus a lot. So you have to revise regularly. Once you do that, it will be like cakewalk. The topic will be like a cakewalk once you understand it properly. Because why there will be confusion will be because you are new to this sinusoidal things, sine, cos terms. You have learned it in 10th class, but you have learned it as just sine of 45, sine 60, these things. But sine function, you have learned, you might have known about functions. We're dealing with sinusoidal functions here. So since you are not familiar with that, this topic might look like little difficult initially, but later when you get used to it, it is not so difficult. Fine. So we've discussed about oscillations, periodic motion in yesterday's class, and we have talked a little bit about what is simple harmonic motion. Okay, a special type of oscillation, we call it as simple harmonic motion. And what is the speciality, or what is the thing about simple harmonic motion? Let's try to understand. The thing about simple harmonic motion is, I've written here, simple harmonic motion is a special case of oscillatory motion in which acceleration or restoring force, say I'm using a new word here, acceleration. Say restoring force can we write it as F means force. Since it is restoring force, I'm writing it as F restoring force. Force, can we write it as mass into acceleration? Can we do that? According to Newton's second law, net force on an object can be written as mass into acceleration. So according to simple harmonic motion, we've learned in yesterday's session that in simple harmonic motion, restoring force is proportional to displacement, is directly proportional to displacement, which we have represented as x, y. Yes, you can take any variable, but generally we go ahead with x or y. So if restoring force is proportional to displacement, we can write restoring force as mass into acceleration. Always acceleration is dependent only on force. If you apply more force, then there will be more acceleration for the object. So we can rewrite restoring force as mass into acceleration, which is proportional to displacement. Now, since mass is a constant, acceleration also can be written as proportional to displacement. The force is displacement means acceleration is also displacement. It's a simple formula because force is mass into acceleration, where mass is a constant. So how force varies, in the similar manner, acceleration also varies, right? So we are saying restoring force or acceleration, both of them at any position is directly proportional to its displacement. Displacement, how is it measured? How is the displacement measured? A particle oscillates with respect to equilibrium position. Okay, a particle oscillates with respect to equilibrium position. Let's say, let me take this. There is a space here. So I'm saying that this is the mean position. This is the mean position. Particle starts oscillating from here. It goes to here. It comes back. And it goes this side and comes back. And this keeps happening. This is what we call as oscillation. Or specifically, if it is satisfying this condition, we call it as simple harmonic motion. If the relation between force and displacement is slightly different than this, then we don't call it, it might be oscillation, but it is not simple harmonic motion. Okay, it is not simple harmonic motion. Okay. Right. Now, how is displacement measured? This is the equilibrium position. This is equilibrium position. This we call it as equilibrium position. What is the meaning of equilibrium position? Can anyone tell me? Yesterday we have discussed about it. What position is called as equilibrium position? Equilibrium means what? The position to which the particle tries to move itself. Whatever is the position towards the particle wants to go, that is equilibrium position. At equilibrium position, how is the force behavior? What is the behavior of force in equilibrium position? Anyone? What is the behavior of equilibrium force? We've discussed it. Position at which net force of the particle, net force on the particle is zero, we call it as equilibrium position. Whenever we talk about equilibrium position, always keep this in mind. At equilibrium position, the net force is zero. There might be forces, but they get balanced at equilibrium position. Okay. At other position, net force is not zero. At other positions, if net force is zero, who will bring it back to equilibrium position? So I'm going back. So at equilibrium position, what happens is net force is zero. Very, very important point. At equilibrium position, always net force is zero. So what am I talking about here? I'm talking about, see, any example of simple harmonic motion, the motion of the particle or objects happens with respect to equilibrium position. It can be simple pendulum. It can be simple pendulum, which is going like this, simple pendulum going like this, or a spring moving like this. When you attach an object to a spring and compress it, then what happens? It expands, compresses. So it keeps on moving to and fro. It keeps on moving to and fro with respect to equilibrium position. Equilibrium position means the position where it can be at rest without any external application of force. It can stay at rest if you don't apply any force. But if you apply some force, what happens is you are giving some energy to it. Because of that energy, it keeps on oscillating. It keeps on oscillating with respect to the equilibrium position. The position in which it was initially at rest. If it is at rest means net force should be zero, no? Initially, whatever is the position at which it is rest, that also we can call it as equilibrium position. Okay. So if you want to understand it in a practical scenario, so from now onwards, I'll draw this kind of diagrams. You should link it to what was happening, like the oscillations I've shown you yesterday. Okay. So for example, I've taken a spring here. I've taken a spring and you have touched a small object to it. Now you have touched a small object to it, something like this, of mass m. Okay. Now try to understand this. This is at rest. Now this is at rest. If it is at rest at this position, we can call this position as equilibrium position. Initially, it was at rest at this position because net force was zero. Now what you do is, you can compress it slightly. You have compressed it, and you just left it. You have compressed it till this point, and you have left it. Then what happens? You have compressed means you have done some work. So in which direction have you applied the force? In this direction we have applied the force on this, correct? On this, we applied the force in this direction. And what is the direction of displacement? Can I say this is the direction of displacement? Is that okay? Force in this direction, displacement also happened in the same direction. So what is the work done? Work done equal to F bar dot S bar, force bar dot S bar. Since F force and displacement are both in the same direction, we can write it as Fs cos theta. Cos theta is cos of zero because force and S are in the same direction. So it will be Fs into cos zero. So F into S. Is it positive? Whatever is the direction of force, same direction displacement happened. So that's why the work done is positive. Whatever external work is done, if it is positive, what happens to the energy of the system? Anyone? What happens to the energy of the system? If external work done is positive, let me write it here, an important point. If external work done is positive, then mechanical energy or energy of the system, we can say, because we have done some work now. Work means what? It is energy only. Our energy we have given. In the form of work we have done, we have given some our energy, our physical energy we have given. So when you do some external work, what happens is mechanical work or total energy of the system increases. But when we do work, generally it gets converted to either potential energy or kinetic energy, one of them, or both of them also. So mechanical energy, whenever somebody says mechanical energy, okay, they are talking about potential energy and kinetic energy combination. Whenever we do a positive work means what? Whatever is the direction of force you are applying, if the displacement also happens in the same direction, that is what is positive work. Sir, always that is what happens? No, that is not what always happens. For example, a person is moving, a person is walking. You push him in the same direction as he is moving. Then what happens? He displaces. He gets displaced. He gets displaced in the same direction with a more higher velocity. Similarly, a person is moving and you apply force in the opposite direction. Then what happens? You apply force in the opposite direction. When you apply force in the opposite direction, what happens? He still moves in the forward direction only. Your force is in the opposite direction, but his displacement, he'll displace a little bit and then he'll stop. His displacement and your force are in the opposite directions. The work done is negative there. When work done is negative, it will reduce the mechanical energy of the system. Correct or not? Just try to understand simply. If work done is positive, then mechanical energy increases. Similarly, the opposite is also true. If my external work done is negative, then mechanical energy decreases. Mechanical energy means either kinetic energy can decrease or potential energy can decrease or both can decrease. And vice versa. I'm writing vice versa. The meaning of vice versa, I hope you know. Try to understand. Bike is moving. You accelerate. What is the meaning of acceleration? The engine is pushing you in the same direction. Engine is pushing you in the same direction. So work is done by the engine. Force is applied by the engine in the same direction as you are moving. Because of that work, what is the displacement? Because of that force applied by the engine, the displacement is happening in the same direction as the bike is moving. Force applied is in the forward direction. Displacement also in the forward direction. So force and displacement in the same direction, then work will be positive. Work done is positive. Because of that work done, what is the change that you are observing in the bike? Okay. Let me take some example. There is a bike and he is moving with some velocity v. Now you apply some force F. So if you apply some force F, what happens? What is the direction of displacement? Because the bike is already moving in this direction. If you apply some force, what happens? It increases its velocity, no? Because of that force, this is the first case. In the second case, this is the initial position. Now, after some time, what you do? You apply some force. You apply some force to the same bike. What happens because of this force? Because of this force, what happens is its velocity increases. Let's say the velocity increases to 2v. Let's say that the velocity is doubled because of that force. You have given that force. You have applied some force. Because of that, its velocity increases. And because of that velocity increase or whatever, finally the displacement happened in the same direction as you have applied the force. Now, in this case, work done is positive. Can we say that much? How much is the work done? That's okay. That we can find it if we want. But here, that's not the target thing that we want to understand here. Is it positive or not? Force and displacement same direction. Work done is positive. Whatever work is done, work done is positive. Work done is positive means what should happen? It should increase. It should increase mechanical energy. Correct? It should increase mechanical energy of the bike. Is it increasing or not? Here, kinetic energy was half mv square. And here, kinetic energy is, what is that? Half m 2v square, 2v whole square, which is 4 times of initial kinetic energy. Did the kinetic energy increase or not? Why did it increase? Because work done is positive. I'll take one more case, okay? in the initial situation, same bike, same velocity in the same direction. Now you have applied some force with the help of engine. Okay, you have applied some force. You can apply it manually or with the help of engine also you can apply. First case is, you can think of the first case as a person is moving it, or a person is applying the force so that it can increase its velocity. That way you can increase, you can think, or a person is, he's pulling the accelerator, he's pushing the accelerator more. So then what happens? It gets accelerated, which means its velocity increases. So this work done, if you are accelerating it, then the work is done by the engine. Whereas some person is pushing, work is done by the person. Okay. Now, to second cases, I'm applying some force in the opposite direction. The bike is moving in one direction, but I'm applying force in the opposite direction. I'm obstructing its velocity, or I'm obstructing its motion. There are two ways in which you can understand this. One, if a bike is moving, I go in the opposite direction and I try to stop it. I apply some force in the opposite direction of the bike. That is one way of looking at it. Or applying a brake. If you apply brake, what happens? Applying brake is like opposite of acceleration. Okay. So when you apply brake, what happens? Deceleration happens, which means acceleration in the opposite direction. So when I apply force in this direction, acceleration is also in the opposite direction, or deceleration is there. So what happens to the bike? Let's say the bike, because of that force, I have applied some force for some time and I've just left it, or I applied some brake for some time and I've left the brake. Now what happens is, let's say the velocity reduced. It can reduce to any amount, but I'm just saying it has reduced by half. Now, is the work done positive or negative? The kinetic energy here is half mv square. What is the kinetic energy? In the second case, after you apply the force in the opposite direction, it is half m v by 2 whole square, which is 1/4 of the kinetic energy which it is initially having. Why is that happening? Because work done. What is the work done? Kinetic energy has reduced, or mechanical energy has reduced. Why did it reduce? Because work done is negative. Because work done is negative, energy reduced. Work done is force into displacement. So force is in this direction. And what is the direction of displacement? When though you applied force, it did not go in your direction. It is still going in the same direction. It is still going in the same direction. Displacement is in the same direction, but still, what happened is its velocity got reduced, but the displacement is still in the same direction. Okay. Force and displacement in this case are in the opposite directions. So work done is Fs cos theta, F bar dot S bar, which is Fs cos theta. Cos theta is cos pi, because the angle between force and displacement is 180 degrees. So it is minus Fs. Is it negative or not? Whenever work done is negative, it reduces the energy of the system. Okay. I hope this part is clear. Did you understand the relation between work done and energy increase or decrease?
Yes, sir.
Yes, sir.
Yes, sir.
And in some cases, here I have shown you the case of how the kinetic energy increases. But I told you, when you do some work, potential energy also can increase or decrease. Potential energy also can increase or decrease. In this example, I've shown you how kinetic energy changes. For example, one more case. I'm taking a ball upwards. Now tell me, its potential energy is increasing or decreasing? Its potential energy is increasing or decreasing? I am lifting the ball. I'm an external person. I'm lifting the ball. What is the direction of my force? I'm applying force in the upward direction. And what is the direction of displacement? Same upward direction. Force and displacement are in the same direction. So work done is positive. When I lift the ball, I'm doing positive work. Because of the positive work, potential energy should increase. And you know that when a ball is lifted to a height h, potential energy increases by mgh. Potential energy is also increasing now in this example, right? So when you do some positive work, potential energy or kinetic energy or both of them can increase. Not can, it will increase. Similarly, when you do negative work, kinetic energy or potential energy or both of them. The total mechanical energy is combination of kinetic and potential energy. That combination will reduce when you do negative work. I hope this part is clear. Next time onwards, whenever you talk about external work done, you should understand how the energy changes. There should not be any confusion about this. This will be used in many chapters, many future chapters also. Okay. Okay, fine. Now let's come back to the topic. Now this is the equilibrium position. Now here we are talking about the spring concept. A mass is attached to it. Now what did we do? We have done some positive work. No, here we've done some positive work. Work done is positive. Work done is positive. If work done is positive, energy of the system has increased or not. Earlier, it has some energy, some initial, let's say, since it is at rest, there is no kinetic energy. Since it is at rest, does not mean potential energy should be zero. It might have some potential energy, we don't know. Initially, the energy is some potential, some initial potential it might have, or potential energy also can be zero also, we don't know. It can, potential energy need not be zero always. The object is at rest means kinetic energy is zero. When the object is at rest, potential energy need not be zero. It can be zero or it can be some negative value or positive value. Potential energy can be negative or positive also. But kinetic energy is always positive because it is related to velocity, half mv square. V square is always a positive value. But potential energy can be negative, positive, it can be zero, it can be anything. If you forgot, you can just recollect. In gravitation chapter, you might have learned minus gmm by r is the formula for potential at a point of potential energy. Gmm by r is the potential energy, right? Minus gmm by r, minus sign is there, so potential energy can be negative also, it can be positive also, it can be zero also. So similarly, you can talk about potential energy of electron revolving around a nucleus. There also, if you have remembered the formula for potential energy of electron, it is some complicated formula. It is like it is also having some minus sign. Okay, minus 13.6 divided by n square is the formula for energy, formula for energy of hydrogen atom. Okay, you learned that in our future chapters, or you might have already learned it in chemistry also. But we will discuss about this nucleus and all, whatever I'm telling you, the energy of electron in an orbit in our second year physics in chapters called modern physics. Right. So the point I'm trying to convey is total energy can be negative. Kinetic energy is always positive. It can never be negative. Potential energy can be anything. It can be positive, neutral, and zero, or positive also. Since potential energy, there is a possibility that potential energy is negative. When you add potential and kinetic energy, the result, combination result, can be positive, can be negative, can be zero also. Because potential energy can be negative. That negative added with positive kinetic energy can become zero or can become positive when kinetic energy dominates, or when potential energy dominates negatively, then the result can be negative also. Fine, whatever. So the point I want to convey is initial energy, potential energy, you can't say it is zero only, always. We can't say that. It might have some potential energy initially. For example, I am doing the spring concept on top of a building which is like 100 meters high. On Burj Khalifa, I'm doing it, which is like 200 meters high. If I'm doing it, if I'm doing the spring experiment on Burj Khalifa, then what happens? If let's say if it is 200 meters height, what is the potential energy of it? Mg into 200, no? It has some potential energy, right? Because of that, at the gravitational force, it has some potential energy. Though it is at rest, though we are not moving it at all, it is having some potential energy. So don't think that the potential energy should be zero when it is at the equilibrium position. It need not be. It can be zero. For convenience, we can assume it to be zero. Many times it can be zero also, but sometimes it cannot be zero. So don't get confused when you see a non-zero potential energy at the equilibrium position. Okay, I'm saying this initially when it is at rest, you have not done any work. Okay, you have not done any work. You have not disturbed the spring. Before creating the oscillations, the energy was U naught, let's say. But if the potential energy was not zero, then it will be, I'm saying just it is U is the notation that we use for potential energy, U naught. Or you can also take it as zero also, no issues. So when you do some work, how did you do the work? You are pressing the spring. You are pressing the spring. When you are pressing the spring, you are doing some work, no? Because you're doing some displacement on this mass. You have done some displacement on this mass by compressing the spring with the help of mass. You have pressed mass and the spring together. Because of that compression, or because the displacement happened, that force into displacement is positive, which means work done is positive. When you do work done, positive work, what happens? It gets converted to mechanical energy. It gets converted to mechanical energy of the system. Mechanical energy means it can, when the work done is positive, it will increase the energy, right? It will increase the mechanical energy. It will increase what energy? It can increase kinetic energy, or it can increase potential energy, or both of them. Anything is fine. Now, whatever is the work done, work that you have done, that is getting stored here. That is getting stored here. So now tell me, once you do this work, what is the energy of the system? Whatever work you have done, you have spent some energy. Energy is always conserved. Whatever energy you have spent, that is converted to another form. The energy that you have spent in pressing the spring, that energy got converted to mechanical energy of that mass. Okay. Now, what is the energy? The energy of the system is now U naught is the initial energy. If you assume the initial energy is not zero, it is U naught plus whatever the work you have done, that is getting added to the total energy of this mass. Because whatever work done you have done, that energy got transferred to that mass. Okay. So when you keep pressing the spring, you have pressed till certain point, and you have just taken your finger off. Immediately when you take the finger off, what is the velocity there? Anyone? What is the velocity at that point? At this place. At this place, what is the velocity? Anybody? Simple concept, simple common sense. I'm not using any formulas here. I'm just asking you a simple question here. I'm pressing the spring. I'm pressing the spring. Once I press the spring, till whatever point I want to press. See this from here. This is the equilibrium position. This is the equilibrium position. So I'm just rubbing this part just to make it look clean. Right. So this is the equilibrium position. You have done some displacement. You have pressed the spring by an amount of, let's say, A. This is the maximum compression that you have done. Now, once you compress it, is it in motion? Is it having some velocity? Once you press it, and you have kept your finger there only, what is the velocity at that point of time?
Zero.
Zero only, no? It's not moving, right? You have pressed it slowly. Now it is zero. Once you remove the finger, what is the velocity then? Then also it is zero, no? Why will it move suddenly? It starts moving, but immediately when you remove the finger, what is the velocity? When you remove the finger,
then also it will be
immediately. I'm just asking immediately. After some time, it will have some velocity. You've pressed the spring. What is the spring trying to do? You've compressed it. It is trying to expand. It is trying to expand. So spring will push the ball outside. Spring will push the ball outside. So what happens? So some force is acting on the spring. When you have compressed like this, what is the force acting on the spring? Restoring force. Spring force, we call it. And so basically, since it is trying to restore its original length, we call it as restoring force. Because it is trying to regain its original length, we are calling it as restoring force. You can also call it as spring force, because that is the force of the spring. So restoring force is acting in this direction, in the opposite direction of our compression. So because of this force, when you have lifted your finger, when you have pressed, at the final point where you want to remove your finger, restoring force is acting. Our force is also acting. They are balanced. Net force is zero. That's why velocity is zero. Now, once you remove the finger, our force is absent, but restoring force is there. When restoring force is there, net force is there. Net force is not zero, which means acceleration will be there. No, correct? Acceleration will be there. When acceleration is there, velocity can change. No, velocity can change. No, v equal to u plus at. You know this formula. V equal to u plus at. But what is the initial velocity here? You have compressed, you have just leaved it. But what is the u value? Initial velocity. Initially, is it moving? Just before you removed it, it is not moving. Just after removing also, immediately after removing also, it will not move. Initial velocity u is 0. But with time, because it has acceleration, it will change the velocity, it will increase the velocity, right? So it will acquire velocity, but not immediately, after some time. Okay, fine. At this position, what is the velocity? 0. Now I have lifted my finger. Now I have lifted my finger. Try to understand the story clearly. Simple story. Once you understand the story, everything else will be easy. So story means every point, what is happening. At each and every point, what is happening, that is what we have to understand. So velocity is 0, correct? So at this position, in the most compressed position, the velocity is 0. So from this line, in this language, you can also understand, you have compressed the spring, the position of the mass is here. When you compressed, the position of the mass is here. Okay. And once you leave it, what happens? It goes through this path, goes like this, and keeps rotating like this, keeps rotating like this. So this point corresponds to this point for me. Next time onwards, we don't need to plot the spring. You just need to plot this path. But you should imagine it like this. Okay. Similarly, you can talk about spring, vertical spring also. Same analysis. The same analysis happens vertical. Right. Since velocity is 0 here, what is kinetic energy at this point? What is the kinetic energy at this point? Anyone?
0.
0, sir.
Excellent. Kinetic energy at this point is 0 because velocity is 0 at the extreme position. Now, since velocity is 0, kinetic energy is 0, what can you say about potential energy? Or total energy is equal to potential energy only, no?
Yes, sir. Yes, sir.
Total energy is potential energy plus kinetic energy, but kinetic energy is 0 here. Okay, the total energy is at the extreme position. Total energy is there in only in the form of potential energy, and total energy is present in the object in the form of potential energy only. Okay, so can I also say that potential energy is maximum here? Okay, so for this one, you have to understand other story also. So why potential energy will be maximum is when you leave it from this position, it will travel through this path, no? It will travel from here towards this position, correct? Now, at this point, will it acquire some velocity? Yes, no? Will it acquire some velocity? By the time it comes from here to here, will it acquire some velocity or not? Because restoring force is there, no? Restoring force is there. Restoring force means restoring acceleration is there. Acceleration means what? Increase in velocity only, no? Right? So here, can I say velocity is not 0? Which means kinetic energy is not 0. Can I say that? So total energy is equal to potential energy plus kinetic energy. Understand carefully. So the total energy, will it remain same everywhere? Yes, no? Total energy, unless you do some external work, total energy will not increase. Initially, it has some energy U naught, let's say, and you have done some work. Because of that work, energy increased. Now the energy increased is combination of work done by you and initial energy, whatever it has. If you assume initial energy is 0, then it will be very easy, because whatever is the work done, that is the energy stored there. The total energy of the system is the amount of work you have done plus initial energy, whatever it has. That is stored in the form of potential energy and kinetic energy. Now, since velocity is not 0 here, kinetic energy is not 0. So kinetic energy will be some value. Whatever is that value, that we'll talk about it later. But for now, just try to understand it is not 0. So it will be some value. But total energy should be same, no? Will the energy change? Energy is conserved, no? You have applied some, you have done some work, you just came out of it. You just came out of it. Whatever work you have done, it has increased its energy. And now you are not disturbing the system. Okay, now system has some energy, that mass has some energy, or that system, spring mass system has some energy, right? that energy, it will not change, unless someone disturbs it with some force. That energy will not change. Total energy will not change. I'm not saying kinetic energy will not change or potential energy will not change, but total energy will not change, or mechanical energy will not change. Okay, when external force is not applied, mechanical energy remains same. You might have learned it, no? Mechanical conservation of mechanical energy happens when there is no external force. Sir, you applied some external force. No, I'm talking about after I apply, some work is done. After that, I've removed my hand. The story is, I'm talking about conservation of mechanical energy after I applied the force, and that is done. After that, so total energy remains constant. I hope you're following it. Total energy remains constant. If total energy remains constant, there is some positive kinetic energy. Now, potential energy, will it be maximum here at this position? Will it be maximum? Yes, no. Think, just think. Energy is being distributed, no, in the form of potential and kinetic. Here, there is no distribution at this place. At this place, there is no distribution. See, velocity is 0. There is no kinetic energy. Whatever total energy is there, that is in the form of only potential energy here. Right? Whereas when the ball is coming here, when the ball is coming here, when the ball is coming here, this place, we are trying to analyze that place. When the ball is here, it has increased its velocity because of this restoring force. The ball has increased its velocity, which means there is some non-zero kinetic energy here. There is non-zero kinetic energy means the total sum should be same everywhere. Total energy should be same everywhere. At every point, it should be same. Why? Because energy should be conserved. When there is no external force, mechanical energy also should be conserved. When there is no external work, if you are not doing any extra work, once I applied force, after that the story is done. My work is done. After that, I'm talking about whatever energy it has, that is conserved. No. So total energy should be conserved. Since there is some positive kinetic energy here, potential energy, has it reduced slightly or not? Compared to this one, potential energy reduced, no? Are you following?
Yes, sir.
Now, yes, again, at this place, what happens now? Can you tell me what happens at this place? Now, the spring further expands to here, till here. From this point to this point, is the restoring force acting or not? Restoring force is acting or not? Spring, you have compressed it until it regains its original length. It will try to expand itself. Correct? So restoring force is acting. So restoring force from this point till this point, restoring force is acting in the same direction. Which is its? That force is always towards, it wants to regain its original length. So the force will act in the direction of expansion. So the force on the mass m is acting in the right side, in the right direction, in the right side direction, in the same direction till it reaches equilibrium point. Once it reaches equilibrium point, till it reaches equilibrium point, restoring force is there, which means acceleration is there. As long as acceleration is there, velocity increases, no? As long as the acceleration is there, acceleration means what? Change in velocity per unit time, no? Whenever acceleration is there, because of acceleration, velocity increases. As you accelerate your bike, velocity increases or not? So the velocity keeps increasing till this point, till this point. At this point, can I say the velocity is maximum? Is it fair to say that velocity is maximum? Why? Because restoring force is acting from this point till this point. It keeps on acting. So acceleration is there from this point till this point. Acceleration is there, which means it keeps on increasing the velocity till this point. Sir, why is it maximum here? It can be maximum some other place, no? Yeah, the reason is at this point, net force or restoring force is 0. So at this point, acceleration has become 0. Following? Why is the acceleration 0 there? Restoring force has become 0. Why restoring force has become 0? Because spring regained its original length. When the spring is having its original length, there is no need for spring to apply restoring force. Spring always tries to restore to its original length. When you expand it, it tries to restore to original length. When you compress it also, it tries to restore to original length. Once it regains its original length, there is no need for the spring to apply restoring force. So it means, and when it comes to this point, this point, restoring force has become 0. So which means acceleration has become 0. Till this point, acceleration was there. Till this point, velocity was increasing. And at this point, acceleration has become 0. When the acceleration has become 0, increase in velocity stopped. Now what happens? So there was some kinetic, so velocity has kept on increasing from this point till this point. Since the velocity has kept on increasing from this point to this point, kinetic energy also kept on increasing. So at this point, kinetic energy, since velocity will be maximum, kinetic energy also will be maximum. I'll give you a little bit more explanation for why velocity is maximum here. But if velocity is maximum, kinetic energy also will be maximum. If kinetic energy is maximum, what can you say about potential energy?
Minimum.
Obviously, right? Because sum of total potential energy and kinetic energy combination is total energy. If potential energy is maximum, when kinetic, see this, when potential energy is maximum at extreme position, and kinetic energy is minimum at extreme position. At extreme position, kinetic energy is minimum. If kinetic energy is minimum, potential energy should be maximum. Because the sum should be same, no? The total should be same. The total is same as its initial potential energy plus the work that we have done to create that oscillation, right? So when potential kinetic energy is maximum at this equilibrium position or mean position, we can say potential energy is minimum. Whenever somebody says equilibrium position, always remember this. At equilibrium position, potential energy is minimum. At equilibrium position, always potential energy is minimum. And in any system, the system always tries to go back to equilibrium position, or the system always tries to go back to the state of minimum potential energy. Always the system tries to arrange itself in such a manner that its potential energy is minimum. Because minimum potential energy case, the state of minimum potential energy is a stable case. When potential energy is minimum, we can call it as a stable equilibrium. We call it as a stable equilibrium. We already are calling it as equilibrium position, no? But when potential energy is minimum, we call it as stable equilibrium. When potential energy is not minimum, we can call it a stable equilibrium. Okay, we'll talk more about these words a little later also. Okay. Now we have understood what is happening here. Now, as it goes, once it gets back to its mean position and it starts moving towards the other side, so will it move to the other side, or will it stop at this place? Will it stop at this place, or will it move to the other side? Will it stop at this place, or will it move to the other side? You have compressed it. It has expanded to its original length. And after that, will it stop? Initially, when it was at rest, nobody disturbs it. It will be at rest only at the original position. But when you have compressed it, you have given some extra energy. You have given some extra energy. So that extra energy got converted to potential energy initially. See this one? Here it got converted to potential energy. Because there is no velocity, the total energy got converted to potential energy. Now, when you released it, what happens? It came back to the original position or equilibrium position. But whatever energy it has, that energy got converted to kinetic energy. See here, it got converted to kinetic energy. Kinetic energy means velocity. When it has velocity, why will it be at rest? Why will it not move to the other side? It has velocity means it will travel to the other direction. No. It's only if its velocity is 0, it will not move to the other side. At this point, velocity is there, and it is the maximum velocity possible. So with that velocity, with that kinetic energy, it tries to move to the other side. It tries to move to the other side. Now, as it keeps moving onto the other side, is the spring getting expanded or not? This is the original length of the spring. Now, as you have compressed, it kept expanding. It got to its original length. And after that, because of that velocity, how did that velocity come? Because of our work. Whatever external work we have done, that has increased the energy of the system. Initially, it is in the form of potential energy, but later it got converted to kinetic energy. Kinetic energy means in the form of velocity, it is there. Right. Because of that velocity, it tries to move on to the other side. As it moves to the other side, what happened to the force? As it moves to the other side, the spring is getting expanded, no? The spring is getting expanded. As the spring gets expanded, its length increases. Compared to its original length, it has increased. When you know about spring, right? When you expand it, what happens? It tries to pull you back. It tries to, it opposes that increase in length. So what happens to the force? When you expand the spring, it tries to pull back. So force acts in the opposite direction of change in length. So since if the length is increasing, at this place, force is acting in this direction. Restoring force acts in this direction. When you expand the spring, let us talk about the third case. Let me plot the diagram. It can come till this point. When it expands, whatever is the length by which it expands, A is the length by which it expanded. Similarly, the A is the length by which it can expand from the equilibrium position. Maximum it can expand is same as A. But as it expands, as it keeps on expanding, how is the restoring force? Restoring force always tries to regain its original length. So in this position, restoring force acts in the opposite direction. Restoring force is trying to pull the spring back to its original length. So not only at this point, at this position, but as it keeps moving from this point to the other side, as it keeps moving from this side onto the other side, the increase in length is there. When the increasing in length is there, restoring force starts acting. From this point till this point, restoring force was always in the same direction, which is towards left. Now restoring force is towards left, but direction of motion is towards right. Direction of motion and restoring force are in the opposite direction, right? Now what happens to it? Because of restoring force, acceleration will be there. Net force is not zero as it moves beyond equilibrium position. You have compressed it, it has come to the mean position, and then it keeps on expanding because of that kinetic energy. It keeps on expanding. Because of that expansion, the spring got expanded, so restoring force is trying to pull it back. So restoring force is in one direction, but it is moving in the other direction. If velocity and force, or velocity and acceleration, are in the opposite direction, can we not call it as deceleration? The object is trying to move in this direction, but restoring force is acting in this direction. Velocity is in this direction, restoring force in the opposite direction. Restoring force is in the opposite direction means acceleration is also in the opposite direction. When force is acting in the opposite direction, what happens is it tries to slow it down. When restoring force or acceleration and velocity are in the opposite direction, acceleration tries to decrease the velocity. When acceleration and velocity are in the same direction, velocity increases. When acceleration and velocity are in the opposite directions, then velocity decreases. So what happens now after this point? After this point, from here till this point, what happened to velocity? Has it reduced or not? V is not Vmax, correct? Has velocity reduced or not? Because when it comes from here to here, from here to here, when it comes from here to here, what is happening? Is the velocity reducing or not? Why is the velocity reducing? Because restoring force is acting in the opposite direction. Acceleration is acting in the opposite direction. So force the velocity got reduced. Can I say that? After this point, restoring force is acting in the opposite direction, which means deceleration is happening. Acceleration is acting in the opposite direction, which means deceleration is happening. So because of deceleration, starting from this point till this end point, velocity keeps on decreasing. Velocity keeps on decreasing. And at what point it will stop? The point at which velocity becomes zero, at that point it will stop, right? At that point it will stop. Now here is the kinetic energy maximum at this point. Anyone? At this point, is the kinetic energy maximum? If you want kinetic energy to be maximum, velocity should be maximum. Is velocity maximum here? No. Velocity is maximum here. After that point, why did it not stay at the same velocity? Because restoring force is acting in the opposite direction. Restoring force is trying to pull it back. Because of restoring force, velocity kept on decreasing. Is that okay? Since velocity is not maximum, kinetic energy is not maximum. Kinetic energy is not same as maximum kinetic energy. So if kinetic energy is not maximum, so which means total energy should be same. Kinetic energy is not maximum. So this point, object at this point should have some potential energy and some kinetic energy. How much is that potential energy, kinetic energy? All that we will learn. We will easily find it out in the next few classes. We will learn that. But right now, just understand the overall story. Right. So at this point, object will have some potential energy and some kinetic energy. Now, as it comes to the extreme position, why am I calling it as extreme position? Because it keeps on moving. It is retarding because of restoring force. It is pulling back. The velocity keeps on decreasing, and at some point it becomes zero. Till it becomes zero, it keeps on moving. No, so at velocity is becomes zero, which means kinetic energy is zero here at the extreme position. And if kinetic energy is zero, potential energy is maximum. Is that okay? Following. Is kinetic energy not zero here also? At this position, this is also extreme position. This is also extreme position. At the extreme positions, the behavior is same. Try to observe. Velocities has become zero. Kinetic energy has become minimum. The total energy present is same as potential energy at the extreme position. Whereas at the equilibrium position, potential energy has become minimum. Don't say zero. Potential energy need not be zero only. It can be some positive or negative value also. Okay, but it is minimum. That much we can say. At the equilibrium position, potential energy is minimum. Whether it is zero or not, that we don't know. Okay, but kinetic energy, we are sure that it is zero. Potential energy, it is minimum at the equilibrium position. At the equilibrium position, potential energy is minimum, but kinetic energy is maximum. Okay, so when you compress, because of restoring force, velocity keeps on increasing till the equilibrium position, and then velocity keeps on decreasing and becomes zero. And then again, restoring force starts pulling it back. So then what happens? From zero velocity, it keeps on increasing. The velocity keeps increasing till equilibrium position, and then it tries to compress. So equilibrium, restoring force acts in the opposite direction. So from here, from the extreme position, velocity keeps increasing till equilibrium, and then it keeps decreasing. It becomes zero, and then it keeps increasing, becomes maximum, and then keeps decreasing. Increases, and becomes maximum, and then decreases, and then increases, decreases. It keeps on happening. Okay. So I hope you understood the whatever is the story I've told you till now. I hope you have understood till this point.
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Right. So this is the story that is happening here. Now let us understand. Restoring force is proportional to displacement. Have you understood this part?
Yes, sir.
The meaning of it is more the displacement or more the compression in the spring, more force is acting. Restoring force depends on how much you compress it or how much you expand it. Correct or not? If you compress it little bit, it will also apply a little bit of force. If you compress it more, it will also apply more force, because when you compress it more, restoring force, when you compress it more, you know that spring exerts more force. As you increase the compression, it increases the force that it exerts on us, right? Similarly, as you expand also, when you expand it more, then it tries to pull it back with more force. So the force that it applies, the spring applies, the restoring force in any SHM motion. SHM motion need not be spring only. In any other case also, it's the same scenario. In SHM, restoring force is always proportional to the displacement. More the displacement, more the restoring force. Now, can you tell me at what points is the restoring force maximum? Anybody? We know the minimum place, no? Where is the restoring force? Zero. Restoring force is zero at equilibrium. Correct? Next. So obviously now you can tell where is the restoring force maximum. From this concept also you can say acceleration or restoring force is proportional to displacement. Wherever is the maximum displacement, that is when you get the maximum restoring force. So maximum displacement happened when you have compressed it to the extreme position or when it has expanded to the extreme position. At the extreme positions, the displacement is maximum. When the displacement is maximum, we get maximum restoring force. So restoring force is maximum here. And here at this extreme position also, restoring force is maximum. Okay. Hope you're following. Very good. Now let's try to understand. So whatever we have discussed here, it is some basics we have talked about work done and change in mechanical energy. Right. In any SHM motion, there are lots of examples for SHM motion, like spring expanding horizontally or vertically, or simple pendulum going this way, that way. There are a lot of examples. We'll talk about it in future classes as well. In any SHM motion, one thing is common. In any SHM motion, the force, some force, when you disturb the equilibrium of the object, when you disturb the equilibrium of the object, if it tries to move to and fro about the equilibrium position, we call it as oscillation. But if that oscillation happens in this manner, the force, when you disturb from equilibrium, some force is trying to pull it towards the equilibrium, some force is trying to pull it towards the equilibrium. That force, since it is trying to restore to equilibrium, since the force, whatever force tries to restore the object to its equilibrium position, that force is what we call as restoring force. It need not be spring only, it can be any other thing. Okay, the force which tries to pull the object to its equilibrium position, that force is equilibrium force. That force can be any force. It can be gravitational force also, based on the situation. It can be gravitational force, it can be spring force, it can be some other force also. So restoring force is proportional to displacement. In any SHM motion, this happens. If it is just oscillatory motion, I can't guarantee this. Only if it is SHM motion, we can guarantee this will happen. So which means restoring force is equal to, whenever there is a proportionality, can we write it as some constant times x? Right? So restoring force and displacement, they are proportional. So I'm just multiplying with some constant k. If you want, you can use some other letter, but they're in textbooks, they're using k, so we are also using k. But there is one more point here. Restoring force is proportional to magnitude of displacement, but it is in the opposite direction of displacement. Correct or not? Is it in the opposite direction of displacement? We have learned that in the previous and yesterday's session also, but once again we will discuss. At this position, what is the displacement? Displacement is always measured from the mean position. Try to understand this. Displacement is always measured from the mean position. Displacement, we should always measure this. Whenever you're talking about displacement, there should be some initial position and final position. The initial position is always the reference position from which you measure the displacement, is always the equilibrium position, is always measured from mean position. Mean means equilibrium position. There are different names for equilibrium position. Mean is another name for it. Okay, now tell me this. At this point, can anyone tell me what is the direction of force? Towards right side or towards left side? At this point, anyone? What is the direction of force? At this point, how is the restoring force acting? At this point, how is the restoring force acting? When you have compressed it, this
Right.
is restoring force is trying to pull it towards equilibrium. Restoring force is always acting towards equilibrium position. Mind this, it's very easy to understand. Restoring force always acts towards equilibrium position. When it is here, restoring force acts in this way. When it is here, restoring force acts in this direction. Restoring force is always towards the equilibrium. When it is here, restoring force is towards the equilibrium. When it is here, restoring force is towards the equilibrium. Always. Force direction is, restoring force direction is from whatever point you're talking about, from that point towards the equilibrium. That is the direction. Restoring force direction is very simple. Now tell me, at this point, what is the direction of displacement? What is the direction of displacement from at this point? Is this the point? You have to measure from the equilibrium position. From equilibrium, from this point, it has gone till this point. So displacement is in the other direction. Force is in the opposite direction. Correct or not? And similarly, you can analyze here also. Displacement is in this direction at this point. At this point, displacement is in this direction, but force is in the opposite direction. Force and displacement, they are always opposite. The reason is force always acts towards the equilibrium. Displacement is always measured from equilibrium. From equilibrium. Okay, so direction of displacement and force are always opposite to each other. Is this point clear?
Yes, sir.
Yes, sir.
We have discussed it in yesterday's session also. See, opposite to the direction of displacement. I've just said the statement yesterday, but today we have analyzed why it is opposite. Okay. So displacement is always measured from mean position. Okay. Right. So restoring force, can we call it as, can we write as mass into acceleration? Is that okay? So
Yes.
can we write acceleration as k by m into x? Is this okay? Is it clear till this point? Simple funda. What did we write first? From this we got this. How did we get this? That is the basic behavior of any SHM. From the basic definition of SHM, we are trying to get this equation. Acceleration is proportional to displacement, or acceleration equal to k by m, some constant times displacement. So this is till this point, I think it's easy to understand. So I'm proceeding further. So x is displacement here, and a is acceleration. So what is the relation between displacement and acceleration? Anyone? What is the relation between displacement and acceleration? Velocity, can we write it as dx by dt? Is that okay? In our third chapter or fourth chapter, you might have learned
Yes.
it as ds by dt. ds by dt is also correct, but instead of s, we are using x here. X is the notation that we are using for.
Then acceleration will be equal to d square x by dt square.
Excellent. So acceleration, can we write it as dv by dt also?
Yes, sir.
Differentiation of velocity also will give you acceleration, or we can also write it as d square x by dt square. In place of v, you substitute this. If you substitute dx by dt in place of v, you get a double differentiation of x, which is d square x by dt square. There you might have learned it as d square s by dt square. S is the displacement there. Instead of s, we are using a different letter here, x. That is the only change. Apart from that, the concept is same, whatever you have learned. Now let's understand. Observe very carefully. Acceleration is equal to k by m into x. I'm writing acceleration as d square x by dt square. dv by dt, can we write it? dv by dt. Acceleration, I'm writing it as dv by dt. On the other side, I'm just leaving it as it is. Now what I'll do is, both sides I will multiply with dx by dt. Is it okay? Or I'll multiplying with velocity on both sides. See, what is dx by dt? Velocity. I'm multiplying with velocity on both sides. The reason is I want to get velocity relation. I know the relation between acceleration and displacement in SHM. In SHM, we know the relation between acceleration and displacement from the basic definition of SHM. But what we want is, we want the relation between velocity and displacement. Can we get it? By doing some adjustments, we can get the relation between velocity and displacement also. We know the relation between acceleration and displacement, which is a straightforward relation from the definition. From that, we are trying to do some adjustments to get relation between velocity and displacement. Now understand this. Can we write it as dx by dt, can I write it as v dv by dt? See this is equal to k by m into x into dx by dt. I hope that this step is clear. I did not do anything much. Dx by dt, this one I'm replacing it with v, because dx by dt is same as velocity. Now I am cancelling this dt on both sides. Observe carefully. So v dv is equal to k by m constant into x dx. Now, are you able to observe the relation between k and x? But there are some differential terms, dv and dx. So shall we integrate both sides? Let's do indefinite integration. Without limits we'll do. Okay. So what is the integration of v dv? What is the integration of v dv? Come on, simple thing. Integration of x dx you might have learned, no? What is it? X square by 2, no? Plus some constant. So instead of x dx, we are seeing v dv. Just change of variable. Instead of x, we are having v. So it will be, instead of x, it will be v square by 2. Instead, integration of x dx is x square by 2. So integration of v dv is v square by 2, which is equal to k by m. What is integration of x dx? X square by 2 plus constant on both sides. Together, I'll write a one constant here. Is it okay? Understood till this point?
Yes, sir.
Yes, sir.
We got a relation between velocity and displacement. Got some beautiful relation between velocity and integration, velocity and displacement, but that's not complete because we don't know this constant. No. Shall we find that constant? To find any constant, once you do integration, once you do indefinite integration, there will be some constant. Okay. That constant, you have to find it. If you want to find that constant, you should know some information about that equation. Whatever you are analyzing, if you know some information, based on that information, you can get that constant. What is the information that we know? Let's try to understand. Let's go back to previous slide. Do we know any relation between velocity and displacement at some places? At some places, do we know the relation between velocity and displacement? At maximum, at peak positions, at extreme positions, what is the velocity? At extreme positions, what is the velocity?
0.
Let's call the distance between the mean position and extreme position as capital A. Is that okay? You can take some other letter also. I am saying that that distance from the equilibrium position to how much you compress, that distance, the maximum compression you have done, that distance, I'm calling it as amplitude. We can call it as amplitude of oscillation. Okay, we can call it as amplitude of oscillation. So if you want to, I can go to the previous slide. We have discussed it yesterday. The maximum displacement of a particle from its mean position is called oscillation. It's called amplitude of oscillation. It's called amplitude of oscillations. Okay. So that displacement, I'm calling it as A, if that is fine. Now at this position, at the peak position, displacement x equal to A, correct? And what is the velocity? Velocity is 0. Can we substitute that? Is it okay? Is it okay? Similarly, at this point also, velocity is 0 and displacement is maximum A. At this point, it is A, whereas at this point, if you take this direction as positive and the other direction will be negative. Only one direction you have to take it as positive, no? If you take the right side direction as positive, then left side direction will be negative. So if you take displacement as plus A here, it should be minus A here, because they are both in opposite directions, no? Or if you take plus A here, it will be minus A here. Fine. So from this understanding, let's substitute. We know some information. We know that at x equal to plus A or minus A also, at x at the other extreme, both extremes, at x equal to plus A or minus A, both extremes, velocity is 0. Let's substitute that. If you substitute that, velocity is 0 when you substitute x with A. See, if you substitute plus A or minus A, since square is there, it should not matter. So what is C here? C is minus k a square by 2m. Now let's rewrite it. What is the relation between velocity and displacement? K by m into x square plus divided by 2 is there. Divided by 2 is also there. V square by 2 divided by 2. The constant c is minus k a square by 2m, or k by m into capital A square divided by 2. Okay, understand carefully from here to here. So now I can cancel everywhere too. Now v square is equal to k by m. I'm taking common. K by m I'm taking common. One second, we have missed something here. What did we miss? Anybody? We missed a minus sign. We missed a minus sign, right? We've discussed about my minus sign. No? Why did we miss it here? We've discussed it so much. Minus sign, because force and displacement are opposite in direction. So we have discussed that, but we forgot to put that minus sign. Okay, minus sign everywhere. Minus sign, minus sign, minus sign. So it should be minus sign here. If it is minus sign here, then C should be having a plus sign. C is plus Ka square by 2m. Okay, is it clear? I hope you're following. One minus sign we missed. I'm just adjusting that minus sign. So this will be plus. Right. Now let me write the result. K by m I'm taking common. Minus x square plus a square, or I can also write it as a square minus x square. Fine. So finally, the answer is whatever we got. What we got is v square is equal to k by m into a square minus x square, or v equal to under root of k by m into root of a square minus x square. Clear till this point? Simple derivation I've done. You might find it little difficult if you are not good with integration, the simple basics of integration. If you don't know, then you might find it difficult, but fine. If you have not very clearly understood this derivation, that's fine. If you know the result, if you have known how you got this result, that is sufficient. But this integration, if you are able to do all this, then it will be better. It will be better. You'll be more confident. Can I move forward? Anybody, any doubts?
No, sir, understood.
Okay. Purnashri, are you following?
Yes, sir.
Rishika?
Yes, sir.
Harsha? Venkateshwarlu?
Yes, sir.
Okay.
Yes, sir.
So I'm moving to the next slide. Okay. So let's continue from here. We've got the velocity now. What is it? What are the relations we have till now? Acceleration and displacement. How they are changing. If you know the displacement, you can find the acceleration. Okay, that relation we have a equal to k by minus k by m into x. Right? We have that relation. Now using that, we have done some mathematical operations and we found the relation between velocity and displacement. Velocity and displacement. Let's understand whether it is correct or not. Shall we understand whether it is correct or not just by checking some values? We know that when displacement is maximum, velocity is 0. So can you substitute maximum displacement here? Substitute x equal to a or minus a. At the extreme positions, see here, at this position or at this position, velocity is 0, no? Right? But at this position, x equal to plus a, and at this position, x equal to minus a, substitute that and see, is it satisfying that? When you substitute x equal to a square minus a square is 0, velocity is 0, we know that. It is satisfying. When you put x equal to minus a, also it is becoming 0. Okay, when you put x equal to 0, at the mean position, x is 0. If you put x equal to 0, you're getting maximum value of velocity. In this equation, what is the maximum possible? The maximum you get when only when x equal to 0. Only when you put x equal to 0, you'll get the maximum value possible. As x increases, the value of v decreases. You can observe it from the equation. Right, next. What did we get in the previous slide? What did we get in the previous slide? I'm just writing here k by m into root of a square minus x square. So we got the relation between velocity and displacement. Using this relation, what can you say? If I ask you some question, see, the oscillation is happening, the SHM is happening at a displacement of a by 2. If I ask you what is the velocity, you can tell using this relation. Substitute x equal to a by 2, you'll get the velocity at a by 2 position. At a by 4 position, if you say at what displacement, what is the velocity, if you want to find, you can find it using this relation. At every point, there will be some velocity and some displacement. But if you know displacement at some position, then you can find the velocity. Or if it's at some position, if you know velocity, then you can find displacement. Okay. Similarly, if you know acceleration and displacement relation, at any point, if you know the displacement, you can find the acceleration. If you know acceleration, you can find the displacement. Right. Now let's go ahead further and let's get the relation between displacement and displacement and time. Okay. So v, I'm writing it as a dv by dt, sorry, dx by dt. Velocity is differentiation of displacement. Displacement, we are using the letter x here. V, I'm writing it as dx by dt, which is root of k by m into root of a square minus x square. So now let me rearrange dx divided by, I'm bringing this root of a square minus x square onto one side, which is root of k by m into dt. See this? Anybody? Now let's integrate both sides. Here this is a function of x and we are integrating with respect to x. Here it's a constant. Here it's a constant. Root of k by m is a constant. You can just put it outside. And what is left is integration of dt. What is integration of dt? That part should be easy. What is integration of dt? Just t. Integration of dt is just t. Integration of dt means integration of 1 dt. It is integration of 1 dt. It is you can think of it as integration of x power 0. It is t plus some constant. Okay. Integration of 1 dx is x plus c. Integration of 1 dz is z plus c. Something like that. So plus some constant. On the right hand side, we have done the integration. Left hand side, are you familiar with this? 1 by root of a square minus x square. Do you know this result? Do you remember this? Yes, no? Or I'll ask you the other way. What is the differentiation of sine inverse of x? Anybody? If you remember differentiations or integration, both are fine. Differentiation of sine inverse of x is root of 1 by root of 1 minus x. Or differentiation of sine inverse of x by a is 1 by root of a square minus x square. So if you differentiate sine inverse of x by a, you got 1 by root of a square minus x square. So if you integrate this, if you integrate that, you get sine inverse of x by a. Okay. Don't worry if you don't remember these formulas. For MPC students, these things for MPC students also, I think this should be difficult because integration is not over for you. You will be learning it in next year. But for BPC students, this integration you might not be comfortable with, but still you might have learned some results initially in the basics of physics classes. So from that basics, okay, for the integration of this is this much. If you know that much, that is sufficient. You don't need to use this integration result every now and then. It's not required. Right. So integration of 1 by root of a square minus x square is sine inverse of x by a. There is no difficulty in what I am doing here. Only if you don't remember this result, because of that you might feel difficulty, but actually it is not difficult. The simple result I'm using here. Clear till this point? Simple simplification I'm doing here. Simple mathematics I'm doing here. X by a is equal to sine inverse. I'm sending it onto the other side. I'm writing it as sine of under root of k by m into t plus c. See, there is no confusion. It's easy part, easy. X equal to a into sine of under root of k by m into t plus constant. Fine. So what did we get now? We got a beautiful relation between displacement at any point with respect to time. You have pressed and left it. After 1 second, it is at some position. After 2 seconds, it is at some other position. At every point of time, at what position is it? At what displacement it is? That we can find using this relation. Okay. Have you understood till this point? Anyone? Any doubts?
No, sir. Understood. Sir.
No,
No,
sir.
If it is clear till this
Understood.
point, can you tell me if there is sinusoidal signal? Yesterday we have discussed about sinusoidal signal. You have understood this. Tell me what is omega here. You know what is omega, right? Whatever
Yes,
is
sir.
beside t, that is what is omega. Correct? In 1 second, how much is the change in angle? That is what is omega. If you put t equal to 0, what is the angle? C. So let instead of C, since it is inside sign, right? I'm just changing the variable here, just for convenience. Okay. Instead of C, let me use some other variable. Can we find that C? We can find it with the help of some condition. If you use some condition, you can find that constant. Let me use a constant as phi, because phase, that's why I'm using phi letter. C is also fine. There's nothing wrong in using C or some other letter also, right? So if you put t at t equal to 0, I'm just trying to explain you what is omega again, once again, if you have not understood clearly yesterday. T equal to 0, what is the angle here? What is angle? What is inside part of sine? Whatever is inside part of sine, we call it as angle or phase. What is that? T equal to 0, if you substitute, this part becomes 0 plus phi. At t equal to 1, how much is the angle? Root of k by m into 1 plus phi. Can you tell me what is the change in angle or change in phase? How much phase changed in 1 second? Can I say it is root of k by m? Initially it is phi, and it has increased by root of k by m. So change in phase is root of k by m per 1 second, per second. Per second, what is the phase change or angle change? Root of k by m. Angular frequency. Angular frequency means angle change or phase change per second. In 1 second, you just observe for 1 second, how much is the phase change? That is what is omega. Angular frequency we call it, or angular velocity also we can call it. Okay, we represent it with, in 1 second, how much is the phase change or angle change? That is what is angular frequency or angular velocity. So since root of k by m is the angle change per second, or simply I told you blindly, whatever is beside t, that itself is omega. So what is omega here? Root of k by m. Correct? Omega is root of k by m. So let's simplify it further. Omega square is equal to k by m. Omega square is equal to k by m. K is equal to m omega square. Is it okay? Can we write it like this? All three are same things. I'm just rearranging and writing. Omega equal to root of k by m. Just remember this much. From this, you can get the other two. So I hope we got what is omega. So can we write it as a into, just to make it look simple, sine of omega t plus phi. Is that okay? That is how we write sinusoidal signals, right? What is this omega? Particularly, it is root of k by m. What is m here? What is m? M is mass of the object that is oscillating or that is doing SHM. M is the mass of object that is doing SHM, or mass of object which is oscillating. And what is K? It is force constant. Whatever restoring force is there, that restoring force constant. For a spring, it is spring constant is same as force constant. So whatever is the force constant that we are using, K is the force constant, right? So instead of root of k by m, I'm just writing just omega. Okay. Now, with the help of this, can we rewrite this one? See, can we write it as omega into root of a square minus x square? It is more easy to remember, right? Can we write omega as omega into v equal to omega into root of a square minus x square? Is that fine? Instead of root of k by m, I'm just writing omega. Similarly, we have written a equal to minus k by m into x. Do you remember in the previous slide we have written? Or f equal to minus k into x. F we have written it as ma. So ma if you send on to the other side, becomes minus k by m into x. But what is k by m? What is k by m? Omega square. Can we write it as minus omega square into x? See this one? Same relations that we have written previously. I'm just trying to simplify it further. Okay, in textbooks, they have started directly with omega square, a equal to minus omega square x. But I just want to show you how k by m has become omega square. So that's why I have used k by m only. Everywhere I'm using root of k by m. But finally, we have understood why root of k by m is same as angular frequency. So once we have understood why root of k by m has become angular frequency, then everywhere we are using omega. See here, the three relations that we got. First relation is this one. From the definition, we got this. From this relation, we got the second one. And from this relation, we got the third relation, which is this one. Three relations we got. This relation between acceleration and displacement, velocity and displacement, relation between displacement and time. Now, from this, can you tell me, can you differentiate both sides? Can you differentiate both sides? dx by dt. What is dx by dt? Differentiation of sine. Differentiation of sine is cos minus a cos of omega t plus phi. I'm just differentiating this function. I think you know about differentiation. Sine differentiation is cos, and differentiation of inside part omega t plus phi. If you differentiate with respect to time, you get omega outside. Now I'm differentiating it once again. Just differentiate this once again. Minus a omega into cos differentiation is sine of omega t plus phi. Sorry, my mistake. Sine differentiation is cos plus cos. Cos differentiation is minus sine, right? Is it okay?
Yes.
Sine differentiation is cos. Cos differentiation is minus sine. And once you differentiate cos, it becomes sine of omega t plus phi. And differentiation of inside part omega t plus phi, if you differentiate, you get another omega. Already one omega is there, another omega. So both of them, if you combine, you can just write it in one place as omega square. I'm just writing it as omega square. A minus a omega square into sine of omega t plus phi. So can I write it as minus omega square if you put it aside? Minus omega square if you put it aside, what is remaining? A sine omega t plus phi. What is a sine omega t plus phi? Is it not same as x? What did we get? We got what we already know. What did we get? D square x by dt square. What is that? Have you recognized it? Double differentiation of displacement. What is it? What is it? Acceleration, right? This is acceleration. I'm just writing it as a. What did we get acceleration as? Minus omega square into x. That we already know. We are not getting anything new here. Okay, but we are trying to play around with sinusoidal signals here. The sine signal is there. We are just differentiated once to get velocity. We differentiated again to get acceleration. So this is acceleration. Now what is dx by dt? What is dx by dt? Velocity. So now we got 1, 2, 3, 4, 5 relations. First relation based on the definition. Second relation is velocity and displacement relation. Next, from that we got displacement and time relation. And then from that, once you differentiate displacement and time relation, you got velocity and time relation. Here, velocity and time relation. We got velocity and time relation. And once you differentiate again, you got acceleration and time relation. Velocity and time, acceleration and time, displacement and time. Three relations. There are only three parameters, three variables here: displacement, velocity, acceleration. The relation between themselves and the relation with time. There is an independent variable, time. The relation of these three variables: acceleration, velocity, and displacement. X, V, A. These are the three variables. And there is an independent variable T. So the relation of displacement with time, velocity with time, acceleration with time, we got it. And the relation between these variables internally, the relation between these two variables, and these two variables, if you can find, you got the relation between all the parameters involved. So we have relation between X and V, correct? We have relation between X and V. We have relation between A and X. A relation between A and X. And we want do we have a relation between V and A? Do we have a relation between V and A? No, right? We want a relation between V and A, correct? We can find that also. We can find the relation between V and A also. How is it? Yeah, from here also we can find it. Let me just go to the next slide. X is equal to A cos omega t plus phi, and V is equal to A omega, differentiation of this is sine of omega t plus phi, right? And acceleration is equal to minus A omega square, whatever we got in the previous slide, I'm just writing here, cos of omega t plus phi. Observe carefully. We can just get the same relations again, once again. So can we write it as A omega into sine theta or sine square theta plus cos square theta? Can we write it as 1? Which means, can we write sine theta as under root of 1 minus cos square theta, or cos theta, can we write it as under root of 1 minus sine square theta? Is that okay? I hope this part should be easy. From this we got this. Now, can we write sine as under root of 1 minus cos square of omega t plus phi? Is that okay? Now, can I send omega in, put it aside, and inside, let's send A inside. If you send A inside, it becomes A square minus A square into cos square omega t plus phi. What is A cos omega t plus phi? A cos omega t plus phi is x square. X is A cos omega t. X square is A square cos square. So we already know this relation. I'm just trying to get it in another way. Okay. Using the same way process, we want to get the relation between acceleration and velocity. Velocity is in terms of sine, but acceleration is in terms of cos. Can you convert cos into sine in the same manner? Minus omega square into under root of A also inside. Now it becomes A square cos square. Can we write it as A square? A inside, it becomes A square. Cos theta, I'm writing it as root of 1 minus sine square. Okay. This 1 omega also just send it inside, because we want A omega sine of omega t plus phi. There is only sine here. A is there. Send on omega also. Not omega square. I'm just sending 1 omega inside. Omega inside root, we can write as root of omega square. This omega into omega, I'm just writing it as under root of omega square. Under root of omega square is omega. Okay. This A square to 1 minus sine square of omega t plus phi. Observe carefully. So it is minus omega into under root of A square omega square minus, what is A square omega square sine square? It is V square. See here, easy. Okay, follow.
Yes. Yes, sir.
Okay. Or can we also write it as velocity? Just look at this one. A is, what is A here? What is A here? Can I say it is maximum displacement? What is the maximum value of displacement possible? Maximum value of cos possible is 1. So maximum value of displacement possible is plus A. Is that okay? Similarly, can you tell me what is the maximum value of velocity possible? Vmax possible is how much? Can we
A
write
omega.
omega? And what is the acceleration maximum possible?
A omega square.
Yes, omega square is the maximum magnitude. Okay, you can write as plus or minus. Magnitude is same, a omega square. When cos is -1, it becomes plus a omega square, and cos is +1, it becomes minus a omega square. So, are you able to observe a square is maximum amplitude square, correct? Minus x square. Following? Next, how about this one? Can we write as minus omega into root of what is a omega? A omega is maximum velocity only, no? Correct? Can we write like this? So we have a relation between every parameter. There are only x, v, a, and t. The different possible relations between these 4 variables we have found. You don't need to by heart them. You don't need to by heart them. We know how to find it in different ways. We know how to find it, relation from one variable to another variable. We know how to find it in different ways. So try to do whatever derivations I have done on your own. Once you do that, you'll get perfect confidence. Okay. You don't need many formulas actually. We will solve the problems in a very easy manner, but you should be understanding how we got it, the process through which we got it. Then you will be very confident. Okay, we may not need to use all the formulas that we have derived, but you should understand the process through which we got them. Okay, well, because if you know the process, even if you forget, you can get through the process, you can get that again. You can get it again within half a minute or 1 minute. You can get the formula that is required. Okay, fine. Then let's stop at this place. There is a lot of discussion pending. We will continue in the next session. Next session maybe tomorrow or day after tomorrow. I'm not sure. I'll update you. We will update you in the WhatsApp group if there is a session tomorrow. Okay, fine then. So we'll stop at this place. Kindly revise the whatever we have discussed till now. Take care and bye-bye.
Thank you, sir.
Thank you, sir.
Thank you.
Yes, sir.
Thank you, sir.
Good night.